The Big Bang Theory says that everything necessary to create all the billions upon billions of stars and galaxies emerged from something smaller than a pea. This is an extraordinary claim, and extraordinary claims require extraordinary evidence to support them. But we don't have extraordinary evidence to support the Big Bang. In fact, at its very start, this singularity cannot be explained by our current understanding of physics and quantum mechanics. Stephen Hawking says, at a singularity, all the laws of physics would have broken down. Theoretical physicist Sean Carroll says, there was a singularity, but there was also a thing called quantum mechanics, which gets in the way. Dr. Sabine Hosenfelder says, we should be using a better theory, one that includes the quantum properties of space. Unfortunately, we don't have a theory for this calculation. And so all we can reliably say is if we extrapolate Einstein's equations back in time, we get the Big Bang singularity. So even at its start, the Big Bang requires us to accept things that are outside of our scientific observations. But what about our scientific observations? Actually, the Big Bang has repeatedly failed to match up with our scientific observations, and it has many failed predictions. The problem is when our scientific observations haven't matched up with the Big Bang model, instead of concluding that the theory might be wrong, hypothetical entities have been invented to salvage the theory. Nearly the entire edifice supporting the Big Bang is now made of processes and energy and stuff that we have not observed and cannot explain. For example, inflation. Inflation is a process by which the universe supposedly expanded exponentially and rapidly, faster than the speed of light, conveniently solving the monopole, horizon, and flatness problems, which crippled the Big Bang. Sir Roger Penrose, Nobel Prize-winning physicist, calls inflation a fantasy. It's just something made up to get the universe to do what you want. For the current model of the Big Bang to be correct, 95% of the universe must be made of ghost matter and energy. Despite great effort, dark matter remains unobserved and unexplained. Dr. Richard Liu says, the irony of today's times is that while dark matter is still unidentified despite half a century of search, taxpayers are asked to invest in yet another potential fiasco. This is the world's most sensitive dark matter detector, and it has found no signs of hypothetical dark matter. The problem is there is circular reasoning when it comes to dark matter. We've got a galaxy problem. The solution is dark matter. How do you know dark matter exists? Because without it, we'd have a galaxy problem. Dark energy. Well, dark energy is a mysterious anti-gravity force which supposedly kicked in just a few billion years ago to help the universe expand faster. No one can tell you what dark energy is. No one can tell you where it came from. And so this is just another hypothetical entity that is needed to support the Big Bang that we have no observational evidence to support. At the very base of the edifice supporting the Big Bang is the idea that the universe is expanding. This is the essential pillar of the Big Bang. Michael Disney, an astrophysicist who has been skeptical of the Big Bang, said that if expansion were to fail, so would the entire superstructure. So without expansion, there is no Big Bang. So what is the evidence for expansion? Now, in the past, I've heard people say that general relativity is evidence for the Big Bang, because general relativity in a homogeneous and isotropic universe would require that the universe would be either expanding or contracting. But general relativity is not evidence for the Big Bang. We don't use theories to back up other theories. We use our observations. And here's a quote from Eric Lerner about general relativity. When someone asked him, doesn't Einstein's theory of general relativity prove that the universe is expanding? He says, a theory can't prove that the universe is expanding. Only observations can. Our observations indicate that the universe is not expanding. Even well-founded theories that make predictions that are proven wrong by observations. Maxwell's theory of electromagnetism, which is still a very well-founded and accurate theory, predicted that atoms would collapse because electrons would spiral into the nucleus. Researchers found that electromagnetic theory had to be extended by quantum mechanics for very small objects. So, since observations indicate that the universe is not expanding, some modifications will no doubt be needed to extend the theory of gravity to very large scales. So, what is the evidence for expansion? Redshift is often used as the main idea supporting the expansion of the universe. Now, redshift is an observation that we make when we look out at distant objects like galaxies. The light that we receive from them is shifted to the red. And we observe that the distant objects, the farther away they are, the more red-shifted they appear. Redshift is observed, but expansion is not. Expansion is an interpretation of the redshift, and a faulty one. Redshift has a correlation with distance, but there is no reason to interpret that correlation as space expanding. In fact, many of our observations with the Hubble telescope and now with the James Webb telescope have provided excellent evidence that space is not expanding. This is from an article in the journal Galaxies that recently came out. The black dots on this chart are previously observed galaxies, and the red dots are galaxies we have observed with JWST. If the universe is expanding, we would expect to see these galaxies plotted along this dotted line toward the top. But the majority of galaxies have angular diameters that fall on the dotted line below, which is the non-expanding model of the universe. Spectroscopic analysis of these galaxies show that they have the same chemical content, number of stars, and type of stars as the galaxies in the local universe. But when we calculate for expansion, we've got to fit all that same stuff in a much more compact space. These galaxies would have to be denser and brighter and smaller than any galaxies we see in the local universe. Some would say impossibly small. If the Big Bang expansion is true, some of these galaxies are impossibly small and dense. For example, this comes from Eric Lerner's channel, LPP Fusion, and he shows this galaxy, this GHZ2. And if we have no calculations added in for expansion, the radius, the luminosity, the surface brightness, and the volume of this galaxy is very similar to galaxies in our local universe. But when we have to add in the calculations for the optical illusion that comes with the Big Bang expansion, this galaxy becomes smaller and brighter, hundreds of times the surface brightness than galaxies in our local universe. And the volume brightness would have to be 14,000 times what we see in the local universe. This is an impossible galaxy under Big Bang expansion. The authors of this article in Galaxies say this about their observations of these JWST galaxies. There is an excessively large number of galaxies at high redshifts, which is not foreseen by the standard cosmological model. Galaxies at these redshifts have disks and bulges, which indicates that they have passed through a long period of evolution, which shouldn't be if they were that close to the beginning of the universe. Spectroscopically, these galaxies resemble their counterparts in the local universe, but they have a very odd thing. The smaller galaxies would be more massive than larger ones, which is quite the opposite of the common view. They conclude that the JWST observations of high redshift objects cannot be explained by the expanding universe model. Here's another paper showing that our observations of these distant galaxies contradict the expanding universe hypothesis. And these galaxies shouldn't even be there. In 1988, Joseph Silk, a prominent astrophysicist, said galaxies have now been discovered at redshifts larger than 3, which is getting quite a way back toward the Big Bang. That's precisely the redshift range you'd expect galaxies to be forming at. Well, that was 1988. And back then, people were saying that there were no formations of galaxies until much later in the universe than the galaxies that we observe now. Look at this NASA diagram. It shows galaxy formation. It shows the first stars forming at about 400 million years, and then the galaxies forming much later. Well, our JWST observations show that we have galaxies that are earlier than the period of those supposed first stars. So according to Big Bang predictions, those galaxies shouldn't be there at all. With the JWST, we are now observing distances that reach all the way back to 250 million years after the supposed Big Bang. We are observing fully formed spiral and elliptical galaxies, which, according to the model, are supposed to take billions of years to form. The Big Bang model also predicts that we would see many galaxy mergers, but we haven't seen the large number of galaxy mergers needed to create the larger galaxies. These galaxies are supposed to have many mergers in order to be able to form into these very large elliptical and spiral galaxies. We haven't seen that. Ivo Labe, the lead author in a recently published study in Nature, saw the data from JWST observations and said, "I nearly spit out my coffee. We just discovered the impossible, impossibly early, impossibly massive galaxies. Those galaxies are only impossible with the Big Bang model." This is from the Nature article that Ivo Labe helped to publish. He says this: if the redshifts and fiducial masses are correct, then the mass density in the most massive galaxies would exceed the total previously estimated mass density by a factor of 2 at Z8 and by a factor of 5 at Z9. At the bottom, you'll notice he says, a more fundamental issue is that these stellar mass densities are difficult to realize in the Big Bang model, the standard LCDM model. Joel Leah, another author in that same article, says, we've been informally calling these objects universe breakers. Well, don't worry, guys. The universe is just fine, but the Big Bang is dead. And here's a list of scientists who agree. And there are actually many more scientists who have signed this letter, this open letter in cosmology. And I just want to read a segment of the letter that they signed with their thoughts about the Big Bang. In cosmology today, doubt and dissent are not tolerated, and young scientists learn to remain silent if they have something to say, something negative to say about the standard Big Bang model. Those who doubt the Big Bang fear that saying so will cost them their funding. Even observations are now interpreted through this biased filter, judged right or wrong depending on whether or not they support the Big Bang. So discordant data on redshifts, lithium and helium abundances, and galaxy distribution, among other topics, are ignored or ridiculed. This reflects a growing dogmatic mindset that is alien to the spirit of free scientific inquiry. Today, virtually all financial and experimental resources in cosmology are devoted to Big Bang studies. Funding comes from only a few sources, and all the peer review committees that control them are dominated by supporters of the Big Bang. As a result, the dominance of the Big Bang within the field has become self-sustaining, irrespective of the scientific validity of the theory.
Big Bang or Big Blunder. Once upon a time, Thomas Henry Huxley, also known as Darwin's Bulldog, said, "The great tragedy of science, the slaying of a beautiful hypothesis by an ugly fact. The great tragedy of science, the slaying of a beautiful hypothesis by an ugly fact." For me, the beautiful hypothesis was the Big Bang Theory, as articulated by Robert Jastrow's book, God and the Astronomers. But over the years, ugly facts have emerged to slay the beautiful hypothesis of the Big Bang. While I was an undergrad at George Mason University, my textbooks taught me of the Big Bang, but there were three prominent physics professors who openly objected to the Big Bang and what their fellow faculty members were teaching me. I went on to study physics in graduate school at Johns Hopkins University. During that time, Adam Riess, a professor at my school, won the Nobel Prize for his supposed discovery of the dark energy anti-gravity force of the Big Bang. Though I celebrated the fact that two professors in the same year from my school won Nobel Prizes in physics and in chemistry in 2011. I lamented that Riess's Nobel Prize might be in vain, since there were whispers among faculty and grad students at his own school and outcries in scientific literature that his conclusions were disconcerting, to say the least. The Big Bang is predicated on the assumption that space is expanding, and this claim is further predicated on the assumption that galaxies are apparently moving away from us in all directions. But are the galaxies really moving away from us, or is this apparent motion an optical illusion created by the interstellar medium of free electron plasmas in space? By way of analogy, here, for example, is an optical illusion of water supposedly bending a pencil. But is the pencil really being bent by the water, or is the water merely causing an optical illusion of bending? And so, by way of analogy, can the interstellar medium composed of sparse free electron plasmas create an optical illusion of motion? The answer is yes. But first, some basics. If I'm speeding, a police officer with a radar gun detects that I'm speeding by using a radar gun to transmit a radar signal at one frequency. And as the radar signal bounces off my car, the frequency of the radar signal is changed from high to low. And this change from high to low is called a redshift of the radar signal. The radar gun then uses the amount of change in frequency or redshift to compute my velocity. Now, Ask yourself, if radar guns don't use the expanding space model of the Big Bang to compute relative velocity from redshifts, then why should astronomers? Should I say to the police officer, "But officer, I wasn't speeding, space was expanding"? Of course not. I wouldn't say that. So even granting there is apparent relative velocity, why even assume expanding space is the cause of the redshift? One can just as well assume something is speeding through non-expanding space. But even worse for the Big Bang expanding space model, the redshift may not even indicate relative velocity because electromagnetic waves traveling through the abundant amounts of photoionized free electron plasmas in space can be redshifted from high to low. This has been experimentally confirmed by numerous experiments, both in laboratories and through space probes flying through the solar system. Holy escargot, Paderewski! That snail is moving close to the speed of light. Easy there, Robin. Since the snail is far, far away, the interstellar medium is confusing the radar gun. The snail is moving at a snail's pace. The radar gun is not accounting for the abundant interstellar free electron plasmas. Therefore, the gun thinks the snail is moving almost at light speed, but it's an illusion of speed. Check out these papers. In other words, shift happens. Shift happens, and that's why the Big Bang is a big blunder. Thank you.
That was great, Sal. Thanks for explaining to us how we can see all this redshift without the universe being expanding. And so now I'd like to explain more about that and why expansion actually causes us to make ridiculous conclusions. So expansion is not only unobserved, it has led to faulty and ridiculous conclusions like dark energy. Here's how dark energy was born. In Sal's opening, he mentioned Adam Riess, who shared the Nobel Prize in Physics in 2011 for the discovery of the accelerating universe. He was doing great work with supernova observations, and I'm grateful for that work. But there was a problem. In his Nobel lecture explaining his discovery, Adam Riess said, "What I initially measured and wrote in my lab notebook in the fall of 1997 was stunning. The only way to match the change in expansion rate I was seeing was to allow the universe to have a negative mass." There was a problem with his calculations. His calculations demanded that the universe have a negative mass. Clearly, the universe doesn't have a negative mass, so something had to be wrong. What is wrong, though, is that he didn't question the presupposition about the expansion of the universe that went into his calculations. So as Adam Riess was doing his calculations, he had to account for expansion. He talks about this in his Nobel lecture when he says that he adds a K correction. And he says, besides causing the redshift, cosmic expansion also dilates time intervals over which supernova light is collected and changes the size of increments in brightness and shifts the portion of the spectrum we observe. That's why he had to add in a correction for that. But the problem is that that resulted in something which is not possible. He says this, "Now my computer programs were telling me that only an imaginary negative mass could match the apparent acceleration and cause reverse attractive gravity." His data made no sense with the expanding universe model, but rather than question the model, he looked for a way to adjust his data with an anti-gravity force. Where would he find such a force? Well, we have to go back in time to Einstein. When Einstein was working out relativity, his equations seemed to predict that the gravity of the universe would cause it to collapse in on itself. He felt he needed to insert something to counteract gravity. So he invented the cosmological constant. It wasn't something that he observed. It was just something he used to keep the universe in a more static state. Now, Einstein said that he always had a bad conscience since he had inserted that cosmological constant into his equations, and eventually he ditched it. But in 1998, when Adam Rees needed an anti-gravity force to cause the universe to accelerate, he resurrected the cosmological constant. So the cosmological constant, which is known as the worst theoretical prediction in the history of physics, is now currently part of our Big Bang model. Why? Because the Big Bang model desperately needs it. And folks, this is how dark energy was born. Dark energy was invented to account for a ridiculous calculation with the expansion model. Without Big Bang expansion, we don't have to invent anti-gravity forces to account for our observations in the universe.
The Big Bang expanding space model fails the angular diameter test. Angular diameter is a measure of the apparent visual size. So the farther the basketball is from the observer, the smaller it will appear, and thus have a smaller angular diameter, as represented by the pink theta symbol. But the basketball's physical size doesn't change, only its apparent size as reflected by the angular diameter. So as a basketball in Euclidean space is moved further and further from us, its angular diameter shrinks. In contrast, in the Big Bang model, an observed object is further and further from us, that is to say more redshifted, its angular diameter doesn't shrink as fast, and in fact at some point will start looking bigger. The point where the object starts to look bigger is known as the angular turnaround point. The Science Asylum YouTube channel covers this, and I credit the Science Asylum YouTube channel for some of these graphics. This is one from that channel, but I added the basketballs there. Actually, the original graphic is like that, where it has the galaxies. Hopefully you get the point. The basketball in pure Euclidean space will, in this graphic, look somewhat like this, not to scale, of course. It'll look somewhat like this. It gets smaller as redshift increases. Whereas the basketball in the Big Bang expanding space model will look somewhat like this, not to scale either. And the basketball in the Euclidean space with a correction for a plasma effect will look somewhat like this. Let's relate the graph from Science Asylum to the graph in the peer-reviewed paper. We can clearly see the actual observed angular diameter points, converge on the predicted Euclidean plasma-corrected model, aka the shift happens model, and not the Big Bang. The Big Bang expanding space model therefore fails because shift happens. And the DNA tests are in, and Edwin Hubble, you are the father of the Big Bang. That ain't my baby, it's someone else's. Edwin Hubble is credited as the father of the expanding space model that is the basis of the Big Bang, but his actual views are more nuanced as articulated in various publications, including this one in the Los Angeles Times, December 31st, 1941. And it says here in the red box, while the expanding theory cannot be abandoned, Dr. Hubble said, present evidence is against it. This leaves the redshift of the light a complete mystery, which still greater telescopes may solve. And yes, telescopes that are out in space, and I alluded to this in photoionized free electron plasmas, but these were quote unquote, really space probes, which are sort of like telescopes, I suppose. And these relate to experiments which I will cover here. The experiment originally was in 1974, and it was virtually ignored, but then revisited in July 2021 and reanalyzed. And this is the paper in the Journal of High Energy Physics, Gravitation, and Cosmology. This is alluding also to that 1974 paper. Same conclusions. So this is a picture of an eclipse by the moon, and you could see the solar corona during this eclipse. It's beautiful. Here is a rendering of the solar corona. The solar corona has lots high density free electron plasmas. It then is a good small scale experiment of what would happen to photons traveling over large distances in much sparser electron plasmas. So we have the Pioneer 6 space probe. It transmits a signal to Earth. As the signal passes through the solar corona, it gets redshifted. The papers involved had to factor out all the relative motion and other kinds of redshifts like gravitational, and the residual indicated a redshift that is caused by the plasmas. This is really bad news for the Big Bang, because there is huge amounts of interstellar plasma. This is experimental proof. It's going to have an effect. No one in the Big Bang community, as far as I know, is doing much to account for this. And maybe if they account for this, there's not going to be any velocity shift left. It will be by the plasmas. And this is what was in the paper. The discovery made in this study on how and why the radio signal under particular physical mathematical conditions undergoes a redshift should not only be considered a local phenomenon on a solar scale, but also a cosmic phenomenon on a larger scale applicable to all stars and galaxies, as it is exclusively dependent on distance of the astronomical object, on the density and temperature of the electrons in the surrounding environment, and on the wavelength of the emitted signal. Also in the paper, it says the Hubble constant represents, for the first time in history, a loss of energy as a function of the fundamental parameters as shown in the following formula. Now, Hubble himself had actually said this much, but this is the first time we have physical experimental evidence to that effect. I will just in passing say some people have said, well, you know, photons traveling through the plasma are going to get blurred. Therefore, it can't be the reason for the redshift. I'm going to counter with the fact this is proof it does redshift it. And since there is so much plasma in space, it has to be the reason it's being redshifted. You cannot avoid it. We have experimental evidence. Our problem then is figuring out why it doesn't blur. But there's absolutely evidence that it will shift. And this can be confirmed also in the laboratory. Now, that being said, there are various modes that redshift can happen. We know that it does redshift, but there are different modes. This is a little bit complicated. So you can have all sorts of materials and it will redshift it, all sorts of materials in different conditions. So we have to kind of parse apart which mechanism is in play in outer space, but it is redshifting it. And the fact that it's not blurring, that's the problem that has to be solved, which is going to be a lot easier than the problems that we see in the Big Bang. So this is it here. Again, just revisiting it. And there are other mechanisms, as I said, modes of redshifting that involve matter interacting with the photons. One of them is called the Wolf shift. Cecil Roy, who was one of those professors at George Mason when I was an undergrad, he objected to the Big Bang, and he says, it has been pointed out by several authors that this mechanism, the Wolf shift, may explain the anomalies observed in observed redshift measurements, especially in the case of quasar astronomy. So here is a situation here. You could see the colored curve there, where the red one is the Doppler shift, and then the Doppler-like shift that's caused by a Wolf shift. So we have two objects that are stationary relative to each other, and because of the Wolf shift, it will be redshifted, and if we didn't account for that, we would think this is velocity-based, and whereas this totally stationary. This is even worse than that crawling snail. These things are stationary. So the Big Bang is wrong because shift happens. It is undeniable. These little straining at gnats and saying, where's the blurring, that's something to be fixed. I mean, that is trivial compared to the camel problems that are in the Big Bang expanding space model.
Thanks for giving us those alternative explanations for redshift, Sal. And, some people might have the question, well, but do our other observations match up with the non-expanding model? And I just want to show this paper from the monthly notices of the Royal Astronomical Society that says that even our supernova data actually matches up with the non-expanding universe model. It says, since the linear hypothesis fits the supernova and local universe distance redshift data, it can be considered as a phenomenological hypothesis. And at this time, no physical model is proposed to explain the linear relation. Now, let's talk about some more failed Big Bang predictions. We've already talked about some failed predictions with galaxy formation and with mergers. And if you want to learn more about some of the recent information that has come out with the JWST that has caused a problem for galaxy formation and mergers, here's an additional article that came out. It's called Panic at the Disks. You can look into that. And one of the things that is said in that article is that our observations of these distant galaxies would challenge our ideas about mergers being a very common process. And so this is a problem for the model, because without that, we don't have a galaxy formation model as part of the Big Bang. And here's an article that I mentioned before. Remember, it's not just that the JWST and Hubble observations are contradicting our ideas about when the galaxies formed and how they formed, but our observations are actually contradicting the idea that the universe is expanding. So you can read more about that in this paper. Now, here's another failed prediction. In 1988, Joseph Selk said, if one measured a gradient or large void that extended over 1,000 megaparsecs, then I think he or she would have to seriously question the Big Bang theory. But we're a long way off from anyone ever claiming that sort of structure. There are only small-scale structures. Well, that was 1988. And since then, we've found structures that exceed the size limit allowed for in the Big Bang model. For example, the giant GRB ring is 1,720 megaparsecs across, was discovered in 2015. Here's what the paper says about it. The recent discoveries of structures exceeding the transition scale of 370 megaparsecs pose a challenge to the cosmological principle. So not only is the structure too large to form in the time that we have for the Big Bang, it also violates the cosmological principle. Now, what is the cosmological principle? That is the idea that the universe is homogeneous and isotropic when viewed from a large enough scale. And so this contradicts that. And there are other large structures which exceed the limits for the Big Bang, the huge large quasar group, and the giant arc. The existence of these structures contradicts the Big Bang model. Lithium abundance is another failed prediction. Here's a chart showing the Big Bang prediction for lithium in the red lines at the top, and the actual observations of lithium fall far below those predictions. The Big Bang has many other failed predictions, and you can find those in this chart in the article by Eric Lerner, Galactic Origins of the Light Elements. Here's a chart showing the references for the Big Bang predictions and then the observations that have been documented that contradict them.
The Big Bang expanding space model may have failed the time dilation test of relativity. I'm just saying may have because there are papers that will say one thing and then another set that will say another. I'm confident, though, that the set of papers I present is actually the real deal. But to be kind of academically responsible, I do have to point out they're still contested. Some of the data I have shared before is not contested. That is not contested at all. This one is contested, and we'll just see where the chips fall on this. But I'm betting that the papers I cite will be vindicated. So we have the theory of relativity, and it actually emerges from electromagnetic theory, which is very well established. It's one of, classical electromagnetic theory within its domain is just like unassailable. It represents the modern world of electricity and magnetism and light, which is a lot of the modern world. Without electricity, you can imagine what your life would be like. And without electromagnetic waves, you'd be dead. So this is a very significant theory. This is an example of a real theory, of a real scientific theory that holds together, that doesn't have all the holes of the Big Bang. Now, from electromagnetic theory, combined with Michelson-Morley, we're able to derive relativity, special relativity. And then from special relativity, it was generalized to general relativity. I actually had to start with Maxwell's equations. My first day in class, the professor assigned, he said, work from these equations. Now, he gave us a lot of help and derive the principle of special relativity as reflected by the Lorentz transformations. So this is just a little chance for me to show off what I learned in school, in that I also accept that relativity is true by and large. Now, this leads to some funny consequences. On the left, at low redshift, this is a picture of a simulation of a gamma ray burst. At low redshift, all the gamma ray bursts will be kind of like under all three models, they'll explode under a certain amount of time. Now, if you look at the toward the right, where it is at high Z, high redshift, the Big Bang model predicts that the gamma ray bursts, these are bursts that occur very energetic at galaxies, the average duration would start to be kind of playing out in slow motion. Whereas in the shift happens model, that is the model that is Euclidean with some correction for plasma effects, there would be no time dilation or no slow motion effect. And the actual data indicates there's no slow motion effect. So which model is correct? I'd say it's not the Big Bang. The correct model is definitely the shift happens model. So here is a little bit from the paper where I got this from, and let's just look at the graph. The plot there is the duration of gamma ray bursts. So at the left is the duration of gamma ray bursts at low redshift, and then toward the right, the higher redshifts. What we should see is that if the Big Bang is true, those measurements should start to converge around that tilted red line. And you'll see that that's predicted. And I have a picture of Leo there as kind of the icon of the Big Bang. And it's not converging on that line. And this does not look good at all for the Big Bang. And you could see the line of the actual data when we average out the effect over redshift. It's almost flatlined. The predicted model says it will be flatlined. So actual results are more in line with the prediction of the Euclidean plasma corrected model. And it is absolutely not in agreement with the Big Bang model. This is devastating. Again, this is the title of the paper. It's an archive. And this is what the author said. Einstein's theory of relativity is quite definite that if the universe is expanding, then the observed duration of these measures will increase with redshift. An analysis of gamma ray burst data shows that the hypothesis of time dilation is rejected. That is, it is false within a high degree of confidence with a probability of 4.4 times 10 to the minus 6th. This is incredible. This is devastating. And then another paper by Crawford that was published in the De Goiter Open journal. He points out this absence of time dilation in supernova data, and I'll explain why this is contested. So in an expanding universe model, you would expect that those dots, which are measurements of, it is a proxy measurement of the duration of the supernova. You could see that the dots do not converge on that red expanding line. Instead, it converges on the blue line. The blue line indicates this, the shift happens, or what he calls the static model of the universe. I mean, the data are just so clearly on the non-expanding Euclidean model. It is rejected for the expanding model. So now, and he says, and I'll explain what the controversy is a little bit in the next slide. Since time dilation is the main defining characteristic of an expanding universe, the conclusion is that the universe does not show the standard time dilation, and these results are consistent with a static universe. Now, I'm going to caution a little bit just so you know what my position is. I would not say necessarily the universe is static forever. I would say it can look static for just the time being, and that's a little bit more complicated. I just want to separate his views from mine. But now on to what the controversy is. We have a lot of papers by even Nobel Prize winners like Saul Perlmutter saying we've confirmed time dilation in the supernova data. Well, you can do that if the data is cherry-picked. All you have to do is take points that lie along the line and then report it. Now, am I accusing them of dishonesty? No. What Crawford did is he found out that their methodology inadvertently used circular reasoning. It ended up picking only the points that would be favorable to time dilation. So therefore, those papers are invalid, and yet they are still accepted. They are still promoted. They are not critically analyzed. And gee, it's going to be really hard to say, man, a Nobel Prize winner just kind of dropped the ball. So how can this be resolved? Well, the data is out there. We can have a conference if people are really serious to re-examine the question critically with qualified experts. I'm not at that level yet, but this data is publicly available. We can look in it, and more papers can be published to reanalyze it. And given all the other problems with the Big Bang, I would have to say I'm going to wager that Crawford is right. And there is a lot of circular reasoning in the Big Bang, in the defense and the apology for the Big Bang. And that's why I have this little graphic there. It says circular reasoning is good because circular reasoning is good. So, and let's go on. That's not the only one. So we have gamma ray bursts. We have the supernova. We also have quasars. And it says here, this is a paper by Hawkins. He says, the main result of the paper is that quasar-like curves do not show the effects of time dilation. Again, this is really bad. We have gamma ray burst, supernova, and now quasars. He does observe there is, however, surprisingly little direct evidence the universe is expanding. He's pointing out there's little direct evidence, and I'd almost say, how about like none? And then you have plenty of contrary evidence, including this absence of time dilation. Now, to be fair, MRS Hawkins is just being a little bit more circumspect in his claims and trying to give both sides a fair representation and say, hey, you know, there's disagreement on this. And that's fine. But I think, you know, the data is the data, and this does not look good for, does not look good at all for the Big Bang. And, you know, again, to be fair, some people claim that Hawkins is wrong. This thing is going to keep going for a while, but let this play out through more observations. And my bet is the Big Bang is a big blunder. Richard Liu, distinguished professor of physics and astronomy, 200 peer-reviewed papers. It's amazing he has succeeded given how outspoken he is against the Big Bang. But you know what? When someone is that talented, people will respect you. They'll keep you in academia because you do good work. And part of that good work has been critical of the Big Bang. And I think maybe some people's conscience are pricked because they know he's saying good things. They would have to be kind of psychopaths to totally suppress his work because it is so good. I mean, one does not attain the title of distinguished professor of physics and astronomy unless one is a distinguished professor, you know, unless one is a distinguished scientist and respected in the field throughout the world. And that is Richard Liu. And this is from a paper he wrote, and I'm sorry I don't have the title there. Hopefully you can Google it. That's one of the best papers against the Big Bang I ever saw, even though it's a little bit dated at this time. He said about the cosmic microwave background radiation, which, by the way, Big Bang proponent says that's proof of the Big Bang. This is what he has to say. The CMB, that is the cosmic microwave background, the CMB temperature was predicted by Big Bang theoreticians. Well, the prediction by Gamow was off by an order of magnitude. Where do you draw the line? How would you like the temperature of your room to be increased tenfold? And there's also this problem of the axis of evil. The axis of evil is a name given to the apparent correlation between the plane of the solar system and aspects of the cosmic microwave background. And the consequence of this is summarized by Lawrence Krauss. The new results are either telling us that all of science is wrong and we're the center of the universe, or maybe the data is simply incorrect. Or maybe it's telling us there's something weird about the microwave background results and that maybe there's something wrong with our theories on larger scales. Yeah, like no kidding, like including maybe the Big Bang. And speaking of Richard Liu, this is a peer-reviewed publication in the Astrophysical Journal of the American Astronomical Society. This is way back in 2005. And the basic thing is the absence of gravitational lensing of the cosmic microwave background. This is very problematic, and I'll explain why. If we look at the cosmic microwave background that is supposed to be in the early universe, as we put our telescopes out there, we should see it. We should see the microwave background kind of here in this curve. And so as the microwave background starts to pass through, the microwaves from that cosmic microwave background passes through all these galaxies, the galaxies should have an effect on those electromagnetic waves. And then here we have this detector here. This represents our detector. And we should, when we see the microwave going through this, we should see the microwave's lens. This is just kind of a picture, like it would be like drops on your windshield. The raindrops on your windshield distort the image. And so these gravitational lenses, the gravity will act like a lens. This is confirmed. This is one of the vindications of Einstein's general relativity. That lens is absent. And some people have been looking for that again. And you could see the figures on the top are what it really is. They had to amplify. They actually had to concoct what it might look like. And you could see this is what it might look like. And they're saying, why aren't we seeing it? We've concluded that there's just all this noise and that's why we can't see it. We actually really want to see this, but we can't. And they're working on the project. I'm just throwing that on the table. The microwave background could be in big trouble. One of the pillars of the Big Bang might, who knows what status it is. But if gravitational lensing is absent, this would suggest then the microwave background isn't all the way behind these galaxies. It might even be local. Holy smokes. And that would be in agreement with the axis of evil that, you know, the microwave background is kind of having anomalies right there on the solar plane. This is really bad for the Big Bang, as if it doesn't have enough troubles itself. And I'll finish on. This is my closing statement. I opened with saying the great tragedy of science is the slaying of a beautiful hypothesis by an ugly fact. I would just amend that and say the great tragedy of science is the slaying of a beautiful hypothesis by a single ugly fact. Einstein said no amount of observations will absolutely prove any theory or his theory, but a single observation can turn it on its head, can destroy it. It can fail on one observation. And so what Big Bang proponents will say is, look at all the good, successful predictions it has. And it's like, I would say, well, even a broken clock is right twice a day. Even a broken clock is right twice a day. A broken clock is accurate to a bazillion places past the decimal point twice a day. This is not the way to form a scientific theory where you just highlight where it's right and then fail to ignore the multiple huge places where it absolutely fails. This is not good science. This is pathetic. This is broken clock science, I would say. And I mean, if things are not worse, this is a complicated topic, and I can only just quote the astronomer here, Michael Disney. He's one of the pioneers in the discovery of low surface brightness galaxies. He's the first to discover a pulsar, first optical pulsar. He's, in other words, a good scientist. And he had this to say: Tolman calculated that the surface brightness, apparent brightness per unit area of receding galaxies should fall off in a particularly dramatic way with redshift. So dramatically, in fact, that those of us building the first cameras for the Hubble Space Telescope in the 1980s were told by cosmologists not to worry about distant galaxies because we simply wouldn't see them. Imagine our surprise, therefore, when every deep Hubble image turned out to have hundreds of apparently distant galaxies scattered all over it. The omens do not necessarily look good for the Tolman test at high redshift. If expansion were to fail, then so would the entire superstructure of the Big Bang. And that was in 2007. Sorry, I typoed the slide there. I miscoded it in the slide. That was 2007 before the James Webb Space Telescope in 2022. This was extremely prophetic because we're seeing all these galaxies at even higher redshift. We shouldn't see them. This is a bad omen. And just to take a little swipe at inflation theory, our opponents in the debate were just advertising how good it was, and it's not that good. In fact, it's looking terrible. In Scientific American, it highlights this. You'll see even sterner things, criticisms, and even Roger Penrose, Nobel Prize winner, saying that it is a fantasy. The author of the article is the Paul J. Steinhardt, is the Albert Einstein Professor of Science at Princeton University. Einstein taught at Princeton University, and the guy occupying his legacy as professor in his place is Paul Steinhardt. He's critical of inflation theory. It's amazing people will put forward things that even Big Bang believers discount as good evidence for their theory. This is terrible. This is like, again, the broken clock. So I will close with saying this, because I think Sir Isaac Newton is prophetically criticizing the Big Bang theory, so to speak. He says, we are certainly not to we are certainly not to relinquish the evidence of experiments for the sake of dreams and vain fictions of our own devising.
And Michael Disney, in his article, Science or Folktale, says this about the Big Bang. In a robust astrophysical field, such as stellar structure, there will be many more confirmatory observations than free parameters. In contemporary cosmology, this turns out not to be the case. Indeed, as we shall see, the number of free parameters probably exceeds the number of relevant independent measurements, as it has done throughout history, and with no sign of convergence between the two. Just because professionals cling to such a flimsy theory, there being no other within their current grasp, need not discourage the rest of us from being a good deal more detached. Let no other try.